Hello everyone, my name is Manar Ibraheem. I'm a PhD student in University of Sfax. I'm so glad to present my paper in the 15th International Conference on applications of graph theory in wireless ad hoc networks and sensor applications And I would like to thank the committee members and the reviewers for their valuable comments and notes. Also, I would like to thank all participants and author and wishing them a good luck. My paper name was the Energy Optimization in Wireless Sensor Networks for Forest Fire Detection, Study of a Sleep Scheduling Technique. The outline of our paper will be the introduction, time scheduling method, MAC protocol, simulation and experiment, and conclusion. In the introduction section, the potential of wireless sensor networks to perform real-time monitoring, early detection, and quick reaction has attracted a lot of interest in the forest fire applications. Energy consumption is crucial in wireless sensor network due to limited resources, and optimizing energy usage become a paramount research objective. In this presentation, we will explore various energy optimization strategies that can enhance the efficiency and the longevity of wireless sensor networks and forest fire detection. We will discuss approaches such as time scheduling methods for sleep and MAC medium protocols that aim to minimize energy consumption while ensuring effective data transmission and network operation. Our research goal needs an intensive investigation of how energy is used by wireless sensor network into service to monitoring for forest fires. By the end of the presentation, you will have a better understanding of the importance of energy optimization in wireless sensor network, challenges involved, and the strategies that can be employed to address these challenges. Together, we can work towards developing more sustainable and efficient monitoring system for forest fire detection. In the time scheduling method for sleep, the sleep schedule is an essential part of energy management. Sleep scheduling strategies strive to reduce power consumption while maintaining the required performance of a network of sensor nodes by synchronizing their sleep and waking times. There are three types of scheduling. The first one was synchronous, the second one was asynchronous, the third one was the hybrid. And the synchronous sleep scheduling involves organizing sensor nodes into clusters and coordinating the wake-up and sleep cycles of nodes within each cluster. This synchronization ensures that only a small percentage of nodes are actively processing data at any given time, while the rest are in sleep mode to conserve power. The low-energy adaptive clustering hierarchy, which known as leech, dynamically selects clusters' heads and rotates their rules, reducing energy consumption spikes and improving resource utilization. This method has been successfully applied in forest fire detection scenarios, effectively extending the network lifespan. In the asynchronous sleep scheduling, often also known as duty cycle, is a method through which nodes may function autonomously without any requirement for central coordination. Each node sets its own schedule for when it sleeps and when it wakes up, using either its own internal data or set of duty cycle parameters. This method enables nodes to save energy in a way that best suits that need and adapts the dynamic nature of network. Adaptive duty cycle is a method of asynchronous sleep scheduling that dynamically modifies the duty cycle in response to external influences and data gathering requirements. To better balance energy efficiency and data quality, nodes may save power during times of inactive while yet responding quickly to urgent situations by altering their sleep active cycles. In the hybrid sleep scheduling, this strategy maximizes energy usage of a wireless sensor network by combining synchronous and asynchronous procedures. In the context of forest fire detection, sleep scheduling strategies are context of forest fire detection. Sleep scheduling strategies are essential for maximizing the network's lifespan and maximizing energy consumption. These approaches enable sensor nodes to conserve energy during periods of low activity while promptly responding to fire events by adjusting their sleep and wake-up times. The choice of sleep scheduling strategy should consider factors such as a network structure, data collection requirements, and desired trade-off between energy usage and network responsiveness. In choosing MAC protocol, by employing effective sleep scheduling strategies, we can enhance energy efficiency in forest fire detection applications. Now let's explore another crucial aspect of energy optimization in wireless sensor network, which is MAC protocols. These protocols govern how nodes access and utilize the shared communication medium, further contributing to energy efficiency. MAC protocols differs in their approach to managing access to the wireless medium and optimizing energy consumption. In wireless sensor networks, MAC protocols play a crucial role in managing access to the wireless medium and optimizing energy consumption in wireless sensor networks. Let's explore three MAC protocols and their unique characteristic, which is the TMAC, Tenable MAC, and Bypass MAC. TMAC means that uses time division multiple access technique to allocate time slots in different nodes in a network. TMAC ensures that only one node transmits at a time to prevent collisions and ensure efficient data transmission. TMAC offers predictable and controlled access to the medium, making it suitable for networks with strike time requirement. Tenable MAC, which is a MAC protocol designed for wireless sensor networks, it is based on the idea of sleep wake-up scheduling, where nodes alternate between active and sleep period to conserve energy. And Tenable MAC uses a randomized sleep scheduling. This randomization approach minimizes collisions and maximizes network efficiency by distributing nodes actively across time. Tenable MAC is particularly effective in scenarios where network traffic patterns are unpredictable or sporadic. And the Bypass MAC, which is the protocol focused on minimizing energy consumption in wireless sensor networks. It achieves this by allowing nodes to bypass the traditional MAC layer and directly transmit data to the sync node by eliminating the overhead association with MAC layer operations and contention-based access methods. Bypass MAC reduces energy consumption in data transmission. This protocol prioritizes energy efficiency and is suitable for networks with centralized sync node architecture. When we will select a MAC protocol, it's essential to evaluate and consider specific requirements and constraints of network application. Each protocol has its advantage, trade-off, and optimal choice depends on factors such as network size, traffic patterns, energy constraints, and latency requirements. In the part of simulation and experiment, to assess the effectiveness of our proposed approach and understand the impact of energy consumption on wireless sensor networks for forest fire detection, we conducted a series of simulations and experiments. These activities aim to evaluate the performance of different MAC, which is the medium access control protocols, and optimize their configuration settings with a wireless sensor network. The simulation we carried out using Omnet++ 4.6 simulation program and with Castalia 3.3 framework, which allowed us to model and analyze the behavior of wireless sensor network under various scenarios. In the first experiment, our objective was to identify the most energy-efficient MAC protocol for the wireless sensor network. We compared multiple MAC protocols and measured their power consumption under the given conditions. The simulations enables us to assess and compare the energy consumption of different MAC protocols and providing insights into their performance and suitability for the WSN. Based on the results of the first experiment, we selected optimal MAC protocol to proceed with the second experiment. The goal of the second experiment was to determine the best configuration settings for the chosen MAC protocol. We adjust and tested different parameters related to MAC protocol, aiming to optimize its performance and energy efficiency within WSN context. Throughout these simulations and experiments, we are able to evaluate the proposed approach, identify the most energy efficient MAC protocol for the wireless sensor network, and fine-tune its configuration. These findings contribute to enhance the efficiency and effectiveness of wireless sensor network in forest fire detection. Here we can see our configuration, how we can divide our area to some clusters. Each cluster contains a head node, which is in a blue color, and the brown color was the sink node. In the experiment 1, we aim to compare the power consumption of wireless sensor networks using different MAC communication protocols and the network parameters we can see here in this table. The initial energy of each node was 18,720 joule, simulation time 2000 milliseconds, number of nodes 20, and the field range 200 by 200 square meters. The MAC protocols that we compared was the tunable MAC, TMAC, bypass MAC, and the round length will be 5 seconds. Through this experiment, we sought to identify the most energy-efficient MAC protocol for our wireless sensor network, which would contribute to optimizing energy consumption. Which would contribute to optimizing energy consumption in forest fire detection applications. From the results in this figure, it's clear that tunable MAC exhibits the lowest power consumption with a value of 87.51909. TMAC follows closely with a power consumption of 89.2338, while bypass MAC consumes the most power with a value of 135.99848. In figure comparison between the power consumption for different MAC protocols based on these findings, it's evident that tunable MAC is the most energy efficient MAC protocol between these 3 protocols tested in our experiment. It consumes the least amount of power, making it a favorable choice for optimizing energy consumption in wireless sensor networks for forest fire detection application. In experiment 2, the goal was to adjust the sleep setting in the Tenable MAC protocol to determine the optimal duty cycle value. The experiment was conducted using 3 scenarios with different number of nodes, which is the 50, 100, and 150 nodes. This variation in node numbers aims to simulate the dynamic environment of a forest fire application. The nodes were uniformly deployed in the network, and the model used for message transmission was based on measuring the temperature at each node. When the temperature exceeds a certain threshold, the node generates a message and sends it to the sink. The network parameters of the second experiment can see in this table. The initial energy at each node will start at 720 joule, simulation time 2000 milliseconds, number of nodes 50, 100, and 150, field range 200 by 200 square meter. The MAC protocol we choose from the first experiment, which is suitable for this type of application, was the Tenable MAC, and the round length was 5 seconds. Now we focus on testing 4 different duty cycle values, which is 0.2, 0.4, 0.6, and 0.8. These duty cycles values represent the ratio of the sleep duration to the active duration for each node. By evaluating the performance and energy efficiency of Tenable MAC with different duty cycle values across the 3 scenarios, we aim to identify the optimal duty cycle that strikes a balance between energy saving and network responsiveness. In the scenario 1, when we use 50 nodes, we can see at the left figure, which is the power consuming, we can note that the consumed power by the network for various duty cycle values. As the duty cycle increases, the power here where increases, the power consumption also increases. The highest power consumption is observed at the duty cycle, which is 0.8, indicating that nodes with longer active period consumes more energy. In the right side figure, we can note the remaining energy. As a duty cycle increase, the remaining energy decrease. This trend that higher duty cycles results in faster energy depletion as nodes are active for longer time and consumes more energy. By analyzing figures, we can a lower duty cycle value can lead to reduced power consumption and better energy preservation. However, it's crucial to strike a balance between energy saving and network responsiveness, considering the specific requirements and constraints of forest fire detection application. In the scenario 2, we used 100 nodes to expand our network, maintaining the same work environment and simulation settings as a scenario 1. This allowed us to compare the network's behavior and energy consumption patterns with an increased number of nodes. On the left side, we can see the consumed power by the network for different duty cycle values similar to scenario 1. And we observed that the power consumption increases as the duty cycle increases. However, the differences in power consumption between duty cycles are relatively small. This suggests that with a larger number of nodes, the power consumption becomes more and across different duty cycle values. And the right side figure display the remaining energy of the network for various duty cycle values. The remaining energy shows a slight decrease as the duty cycle increases. Although the decrease is not significant, it indicates that higher duty cycles still lead to a gradual depletion of energy over time. Comparing the results of the scenario 2 with those of scenario 1, we can observe that trends in power consumption and remaining energy remain consistent with an increase of number of nodes. However, it's important to note that the actual value may differ due to larger number of network size. In scenario 3, we use 150 nodes to further expand the network with 150 nodes while maintaining the same work environmental simulation settings as scenario 1 and 2. This allows us to observe the impact of an even larger size of the network on energy consumption and overall network performance. And the left side figure illustrates the power consumed, and the right side the remaining energy. We can see that the higher duty cycle lead to an increase in power consumption, while the increasing of duty cycle decreases the remaining energy. By comparing these results of scenario 3 with those of scenario 1 and 2, we can observe that the trend in power consumption and remaining energy remains consistent with an increased number of nodes. However, it is essential to note that actual values may differ due to larger network size. These findings emphasize the importance of carefully selecting the duty cycle value based on specific requirements and constraints of the forest fire application. Considerations such as power consumption, remaining energy, network responsiveness should be taken into account to achieve an optimal balance in energy management and network performance. In the results, the analysis of the three scenarios highlights important insights regarding the relationship between duty cycles, power consumption, and remaining energy in WSN for forest fire detection. By carefully selecting the duty cycle value, it's possible to strike a balance between energy saving and data transmission efficiency. The results show that increasing the duty cycle leads to higher power consumption and decreases remaining energy, emphasizing the trade-off between energy conservation and data transfer efficiency. An optimal duty cycle value such as 0.6 here can be chosen to achieve a balance between these factors. Comparing the scenarios with different number of nodes, it's observed that larger network generally exhibits slightly higher power consumption. This is attributed to increased data traffic and processing requirements. However, the impact of remaining energy is relatively consistent across scenarios. The practical implications of this simulation study are significant for energy-efficient forest fire detection systems. The insights gained from understanding the relationship between duty cycle values, power consumption, and remaining energy can inform the design of more effective protocols and algorithms. This knowledge can help prolong the lifespan of sensor nodes and optimize network stability in real-world deployments. It's important to acknowledge the limitations of the proposed system, including the simplified network model used and the assumption of homogeneous nodes. These limitations may not fully capture the complexities of real-world scenarios. Additionally, the lack of real-world deployment validation and the need for further optimization indicates areas for improvement in future research and development efforts. Overall, this simulation study serves as a valuable tool for evaluating the optimizing the energy efficiency of wireless sensor networks in forest fire detection. The findings contribute to the outgoing endeavor, the development sustainable and effective monitoring system for mitigating the impact of forest fire detection. In the conclusion, the research focuses on examining the complex relation between energy use and the performance in network sensor, wireless sensor network for forest fire detection by employing sleep-based concepts and analyze changes in power consumption. The aim is to maximize power efficiency and enhance the effectiveness of the forest fire monitoring system. The findings of this research have several potential benefits, including the development of more reliable networks, longer sensor node lifespans, and reduced damage from forest fires. This can be achieved through the design of energy-efficient protocols, algorithms, and approaches. Achieving a balance between fast data transfer and low power consumption is crucial for the widespread adoption of WSN in forest fire monitoring. Since electricity availability is often unreliable in forested areas, battery-powered sensor nodes are commonly used. Managing the optimizing energy consumption is essential to ensure prolonged node operation with minimal maintenance and monitoring interruption. By addressing the energy consumption challenge, forest fire monitoring system can become more effective and reliable. The implications of this study are significant for the planning, implementation, and management of wireless sensor network during forest fire. The acquired knowledge enables to develop the protocols, algorithms, strategies, as we said, and minimize network's energy damage. Consequently, this increases sensor nodes lifespan, strengthens network reliability, and mitigates the impact of forest fire. The research findings and recommendations derived from the Omnet++ simulation platform are valuable for researchers and practitioners in the fields of wireless sensor networks and forest fire management. The aim is to contribute to the development of long-term, dependable forest fire monitoring system that can save lives, protect habitats, and preserve species by addressing the crucial issue of energy consumption. Future work can explore several areas to enhance the effectiveness of the research. Real-world deployment validation would provide valuable insights into systems performance and reliability in practical forest fire monitoring scenarios. The development of the adaptive duty cycle optimizing algorithms could dynamically adjust energy consumption based on real-time network conditions, further improving energy efficiency and network performance. Thank you for your listening, and if there is any questions.